I want to work through some of the mathematics of if you have a wire and you have, say, a current that has a value I flowing through the wire, what the resulting magnetic field would be. And then if you had, say, two wires, what that resulting magnetic field would be. And I want to work out how you would both calculate the magnitude of that net magnetic field, but also the direction. And the latter involves what is sometimes called the right-hand rule. So before I go any further, right now you're staring at a two-dimensional screen. And so traditionally we think of, say, an X for horizontal and a Y for vertical. But we have three spatial dimensions. And so a way that I'd like you to think about how you would represent on two dimensions what are actually three spatial dimensions. Imagine, say, you had an arrow. So let's say that you had an arrow that has a pointed tip and then has like a cross on the other side of it. So if you can imagine, like if somebody took a bow and shot an arrow at you, if the arrow was coming right at you, you would see the tip of the arrow. And so think of a dot as representing coming out of the screen that you're looking at right now. Now, if instead, like the arrow was fired in the opposite direction, you would see it moving away. And if you see it moving away, you would see that cross on the other side of it. Okay, so think of a dot as coming out of the page and think of the cross as going into the page. So going back to the traditional X for horizontal, Y for vertical, you can think of the Z-axis as coming out of the page or out on the screen as you see it. So with that in mind, I want to introduce you to the idea of the right-hand rule, which is going to allow us to determine in which directions the magnetic field are when you have charge flowing along a wire, i.e., you have current. And so if, for example, so this wire that I have drawn here on the left, imagine we were looking down the wire. If we were looking straight down the wire and the current was coming towards us, it would be a dot. It would be coming out of the screen. And so imagine you took your thumb and you put your thumb in the direction the charge was moving, which is to say your thumb would be pointing up. It would be pointing out of the screen. So the convention, the right-hand rule for the magnetic field due to current is that you take your thumb, you move it in the direction of the charge, and then you curl your fingers. Pretend you're curling your fingers around the wire. The direction of the curl your fingers is the direction of the magnetic field. So more specifically, if my thumb was coming out of the screen, and I have this magnetic field that is surrounding the wire due to the moving charge, then the direction of the curl of my fingers is going to be counterclockwise, like so. If instead I was looking down the wire in the other direction, then I'm going to put an X for it going into the screen. Again, you're going to get a magnetic field that circles the wire. But imagine now my thumb is going into the screen. If I curl my fingers now, again, this is with the right hand. You have to reverse everything. That's with the left hand. If I take my right thumb and I put it into the screen and then I curl my fingers, well, now I'm going to be curling in a clockwise fashion. So that's how you use the right hand rule to think about what direction the magnetic field is when you have a current carrying wire. So let's now go back to the idea that we have a wire in the upper left-hand corner, and that wire has current that's flowing to the left. So if that current is flowing to the left, I would take my thumb and I would move it to the left and curl my right hand around the wire, which is to say that above the wire, the magnetic field would be going in to the screen. And as it wraps around on the bottom of the wire, it would be coming out of the screen. So then let's say I have another wire. And let's say that that has, and I'll call this I1. And now let's say that we have some current I2. And let's for now say they're moving in the same direction. So similarly, above the second wire, you would have, and let me make it a different color just to be clear. Let's go ahead and make it green. So now I'm on the bottom wire. As my thumb moves to the left and I curl my hand around the wire, again, this is my right hand I'm doing this with, then the magnetic field due to the current in the second wire would be going into the page on top, and it would be coming out of the page or out of the screen on bottom. So you can see in between the two wires, you have opposite magnetic field directions. And when you have opposite magnetic field directions, that means that the wires are going to attract each other, which is to say that if the current in both wires is in the same direction, the wires are going to be attracted towards each other. But let's like hypothetically say instead we had two wires, and we'll have one, the current going left again. But now let's have in the other wire the current going right. So again, by the right hand rule, take my thumb, move it to the left, curl around the wire. It's going into the page. On top of that wire, it's coming out of the page below that wire. But now with the second wire, now my thumb is going to the right. And as I curl my hands, now above the wire, it would be coming out of the page or out of the screen. And below it, it would be going in. So do you see now the magnetic field in between the wires is in the same direction? And so that is to say that the wires would actually repel each other. So in this situation here, the wires are going to want to move towards each other. And in this situation here, the wires are going to want to move away from each other. And so to what extent is the magnetic field adding up here? When you have a wire and it has some current I going through it, we say that the B field created due to that current carrying wire is equal to mu naught I over 2 pi r, where r is going to be the distance to some point from the wire. This is sometimes called the Biot-Savart law. And so mu naught is going to be what is sometimes called the permeability of free space, which is the extent to which a magnetic field is able to propagate in a vacuum. So you could probably imagine that for different materials, this value is going to be different. But when you see the mu naught, it means for a vacuum. And so for the permeability of free space, this is defined as 4 pi times 10 to the minus 7 Tesla. And Tesla is the unit for magnetic field, multiplied by meters per amps. Amps is the unit for current. Okay. So for example, if you were interested in figuring out what the magnetic field is at this point right here, well, you have this distance R1 from the first wire, and then you have this other distance R2 from the second wire. And so the net would be equal to mu naught I1 over 2 pi R1 plus mu naught I2 over 2 pi R2. Now here's the key. So when you add the two terms, essentially it's a superposition. At this point X, you're looking for the superposition of the two magnetic fields due to the two wires. But you also have to take into account the sign of these magnetic fields. That's where the right-hand rule comes in. And so that's going to determine whether you're going to have a plus or a minus. And so we're going to define Z as positive when it comes out of the screen. And so you can see that the magnetic fields due to both of these wires, which you see right here, you see those two dots, it's like the arrow coming towards you, it's out of the screen. So in this particular case, you would add the two. But what if you say you change the direction of one of them? Let's say, for instance, I took I2 and instead had it go this way. That is what we had originally up here. Well, in that particular case, then you're going to actually change the sign of the magnetic field. And so this would become a minus instead. So it's not enough using the Biot Savart just to add the two. You also have to think about what direction the magnetic fields are going. And to do that, you use the right-hand rule.